In this video, I'm going to go through an example of a phase line problem. I'm going to use the differential equation dy dt equal minus 2y cubed plus 9y squared minus 12y. So we'll figure out what the phase line for this equation looks like, and then we'll draw a particular solution y against t for the initial condition y of 0 equal 3. So let's go over to another page here. And here we have the equation written out with the initial condition. So our first step is to find the steady states. And the steady states, we take the right-hand side, which I'll call f of y, and we find when it's equal to 0. And those values of y will correspond to constant solutions or steady state solutions of the equation. So here we have a y throughout, so we can factor out a y, and we know that y equals 0 will be one solution, and the remaining equation, once we've factored out that y, will be minus 2y squared plus 9y minus 12 equals 0. And if we check this, now you might want to go through completely and try and figure this out, but if you just look at the discriminant from the quadratic equation, you'll find that b squared in this case is 81. And we have 4ac is 4 times 2 is 8. Minus and minus is a plus, so I have 8 times 12 is 96. So you can see that the discriminant will be negative, so there are no other roots, so there's only one steady state. And there it is, y equals 0. So to figure out what this function looks like in more detail, so that we can draw the phase line accurately, let's also find any critical points. We have minus 6y squared plus 18y minus 12 equals 0. And there's a factor of minus 6 common across here, so if I divide through by that, it'll simplify things a bit. So we have a y squared minus 3y plus 2 equals 0, and that factors y minus 2, y minus 1. And so our steady state, sorry, not our steady states, our max and mins in f of y will be y equal 1 and y equal 2. So we can start drawing the phase line. If we just draw the y-axis here, actually I won't put an arrow on the y-axis because arrows have a different meaning in this situation. And so now I'm going to draw the vertical axis, and that will be, let's move this out of the way. So that will be y prime. And now we know that we go through the origin. We know it's a cubic that opens, or that starts at plus infinity off this direction and goes to minus infinity over here. So we have this coming down. Oops. We know there's no other root, but it has two critical points. And given that it's a cubic, the only option is for this one to be a min and this to be a max. Now, to be careful about that, you can take a second derivative and check, but I won't go through that calculation here because that's not the focus of this video. Let's just skip over that detail for now. And so, what does this, actually we can keep this here. What does this tell us about the way y is changing? So for any positive value of y, we can see that y prime is negative because the graph is below the axis. And in some places, y prime is more negative, large quantity. So we put a large arrow where the slope is very negative, and that means moving to the left with a large velocity. But then as we move to the left, you'll notice that the slope function here, the function that gives us the y prime value, actually increases to a maximum negative number. A large is negative, which means smaller velocity to the left, or small arrow here, and small slope when we start drawing the slope field and the solutions. And then as I move further again, the speed or the velocity gets larger in the negative direction, so these arrows get bigger again. So slightly bigger here, and then biggest here, where I have the most negative number, and then we get smaller again as I get closer. And here I can fill in. So you can see here there's a big arrow, smaller, smallest arrow locally at least, all moving to the left, and then the arrows get bigger again and then smaller as I get close to my steady state here. On the other side, we have a large positive slope, so I put a large arrow out here, and then that is getting smaller as I get closer to the origin. And you can see now that this will definitely be a stable steady state, so I fill it in like that. And so here you can see the overall shape of the phase line. So let's translate that into a solution. So first, now where did this min and this max appear? This one happened at y equal 1. And this one was at y equal 2. So we're starting off at y equal 3 with our initial condition, so that means we're all the way out here. So in words, what does that mean the solution will be doing? So it'll decrease, so the solution decreases rapidly at first, then slows, still decreasing, then speeds up again, still decreasing, and finally slows as it approaches y equals 0. Okay, so that's the word description, what we see here. We start off with a rapid negative direction, so rapid decrease, and then gradually slowing to some maximal slope in the negative direction, so a high point negatively speaking, and then we continue to a much steeper point down here and then slowing again. So now that we know that these are two important spots, we should get a vertical height for these. And so what is y of 1? So I go back up here and I plug in 1 and I get minus 2 plus 9 minus 12. And so that's minus 14 plus 9 is minus 5. So the slope at 1 should be minus 5. So that's the steepest slope we're going to see. Perhaps out here it'll start off steeper. We'll see that in a moment. At y equal 2, what is that slope? So now at y equal 2, so that's 2 to the 4 of 16 is minus 16, plus 9 times 4 is 36, minus 12 times 2 is 24. So this gives me 12 and subtract 16 and I get minus 4. So this high point here is at minus 4. And then what about at y equal 3? Y equal 3, this is 3 times 3 is 9 times 3 is 27, multiplied by 2 is minus 54, plus 9 times 9 is 81, minus 3 times 12 is 36. And so when we add this one and this one, we get 80, 90. So minus 90 plus 81 is minus 9. So we start off out here at y equal 3 with a slope of, now obviously this is not an accurate drawing, but here we're going to be at minus 9. So that should be quite a bit lower down. So now let's put this on a y versus t graph. So we have y of t up here, and we have t going off in this direction. And I think because we're always decreasing, we're going to go from, let's see, we're going to go from 3 down to 0. So I can drop this all the way down here. And we start off at 3. 2 and 1 are going to be important points along the way. Here we start off with a very steep slope of minus 9. And then what happens? Between 3 and 2, we're going to gradually decrease the slope, still negative, but it's getting lower angles, so it mellows out until it hits minus 4 right here. And then after 2, it's going to steepen again to minus 5. So it steepens after that point to minus 5. And then from that point on, it just gets mellower until you approach the steady state at 0. So you can see here, I've tried to make it a little bit more clear, but on this computer drawing it's a little bit tricky. The overall shape though is here it's concave up because the slope is decreasing, or at least getting mellower, so it's increasing but from the negative direction, until at this point here it hits the least steep. It hits this high point in the negative values and then turns around and gets steeper in the negative direction again. So we have concave up here, inflection point, and then concave down. And then at y=1 we have another switch where the slope is, the slope is increasing until it, or steepening in the negative direction, till it hits its most negative slope, and then it comes back up again. And that's what happens after this point here where y is equal to 1. So we have an inflection point here and an inflection point here. And the slope at this point should be m equal -4, and here it should be m equal -5. And then it mellows out to 0 as we approach the steady state at 0. So a way to see this formally that this is an inflection point is by taking the second derivative of y with respect to time. And we know up here that y plugged into this function gives us the value of dy dt, so I actually have to take the derivative of this expression with respect to time. And that I need a chain rule for that, so I'm going to take -3y squared plus 18y minus 12, and then by the chain rule I have to take the derivative of the function inside, which is y, so this is multiplied by dy dt. When is d squared y dt squared equal to 0? Either dy dt is equal to 0, but that's only equal to 0 if we're at a steady state. And we know that that only occurs at y=0. So in our situation where we're not right at the steady state, we have to look at this to see whether we have a second derivative 0. And so the roots of this equation are the ones I'm interested in, and those will occur exactly where the min and max of f of y occurred, because that's exactly f prime of y. So we know that the inflection points, at least potential inflection points, and we have to check it as we're supposed to have done here to make sure, and I'll skip that for now, but these inflection points should be at y=1 and y=2. Which is exactly what we see here. Now I don't know exactly what time they occur at, so I'm leaving that aspect out of this drawing. But I should get the heights correct, and I should try and get the slopes roughly correct.